So, welcome back to lectures on engineering mathematics 2, and this is lecture number 36 on Fourier series for even and odd functions. So, in this lecture we will first discuss what are the even and odd functions again, and then the evaluation of the Fourier coefficients and hence the Fourier series for even and odd functions. We have already discussed in one of the earlier lectures that if the function, the given function is even or odd, then the corresponding Fourier series becomes simpler. So, it will have either only sine terms or cosine terms. So, now coming to the even and odd functions. So, a function is said to be an even function about the point a if we have this condition that if a minus x is equal to f a plus x for all x, then we call that the function is an even function. On the other hand, we call the function an odd function about the point a if f a minus x is equal to minus f a plus x, and that is for all x. So, that is the odd function. So, usually when we in many example we will see that this a is just 0. So, what we have that f minus x is equal to f x for even function and f minus x is equal to minus f x for odd function when a is 0. So, when we are talking about x equal to 0, so the y axis. Well, so there is a property of these even and odd functions. So, the product of two even or two odd functions is again an even function because of that minus sign. So, minus if multiplied by minus is again plus. So, this property holds for if we take two even functions, their product will be also even, or if we take two odd functions, their product will be also an odd function. So, that property exactly will be used for evaluating Fourier coefficients. And moreover, the product of an even function and an odd function. So, if we have in the product one function is even and the other one is odd, in that case the product will be again an odd function. Well, so having these properties of even and odd function, we will now evaluate or simplify the Fourier coefficients for such functions. So, suppose we have this a n given by this integral 1 over pi minus pi to pi f x cos n x dx. Just for simplicity again we are considering this minus pi to pi, but we can also talk about minus L to L and then cos n pi x over L, and there the outside term will be 1 over L. So, just for simplicity we are talking about the interval minus pi to pi. So, if this function f x is an even function, so what will happen, the cos is an even function. So, the cos here is even, and if this function f x is even function, then the product is again even, and in that case the integrand here, the whole integrand is an even function. So, minus pi to pi, this integral can be written as integral 0 to pi and then 2 times. So, the 2 over pi will come outside, and then we have this integral for when f is even, and if s is odd. So, if f is odd and then we have even, so the product is again odd, and in that case since the integral is minus pi to pi, then this will be 0. So, if f is an odd function about 0, this integral will become 0, meaning the a n's will become 0, and if f is an even function, then those a n we can simply compute with the help of this rather simplified integral. So, now integral is varying from 0 to pi only instead of minus pi to pi. A similar situation happens for b n as well. So, if this f x is even for instance and the corresponding sign is an odd here. So, the integrand is odd, and in that case this integral will become 0. So, when f is even, the integral for Bn or the coefficients, the Fourier coefficients Bn's will become 0, and the other one will be simplified the 2 times, and then 0 to pi f x sin n x dx. So, what we have here, that if a function is odd or the function is even, then the corresponding Fourier series either will have only the Bn's terms or it will have only the An's terms. So, when f is even, we will get only the An's, the coefficient An's, and when f is odd, we will get the coefficients Bn, and the correspondingly the Fourier series will be simplified, because in case of the even, when we have only the An's there. So, we have only the cos term in the Fourier series, and when the function is an odd function. So, we will have only the Bn's there, and hence the Fourier series will contain only sine terms. So, that is the simplification for even and odd functions we are going to discuss now in context of the Fourier series. So, we assume that f is a piecewise continuous function on this interval minus pi to pi. Again, for simplicity, we are taking minus pi to pi. All these results can be extended for a general integral minus L to L. So, in that case, if f is an even function, then the Fourier series takes the following simple form. So, if it is an even function, we have only the An's, the Fourier coefficients An will survive, the Bn's will become 0, and therefore, in the Fourier series we will see only the cos term. So, the Fourier series will be simplified to this a by 2, and then having only the cosine terms, where this An can be computed with this integral 2 over pi 0 to pi f x cos n x dx. And such a series is called cosine series, because we have only the cosine terms in the series, and therefore, we call such a series as cosine series. If f is an odd function, so if f is an odd function, then the Fourier series will be simplified again, and since this f is odd, the Bn's will survive, all An's will become 0. That means, in the Fourier series we will have only the sine terms. That means, n goes 1 to infinity, and Bn sin n x will be the Fourier series, and the Bn we can compute with this help of rather simplified formula, where the integral goes from 0 to pi, and there is a factor 2 there. So, 2 over pi 0 to pi and f x sin n x dx. So, these results can be also considered when we have minus L to L, for example, the interval. So, here this n x will be simply n pi x over L, and this integral here, instead of pi we will have just L, and again here n x will be n pi x over L. So, this will be more general formula. So, again the cosine series, for the sine series it will take the form. So, n pi x over L here, and then the L, and then we have L there, and again here for n x we have n pi x over L. So, these changes will be more made, and then we have more general Fourier cosine or Fourier sine series for the function which are odd and even respectively. So, well, such a series is called the sine series. So, now we can discuss some examples based on this simplification. So, for instance, we want to represent this function here f x, which is given by x and 2 pi minus x in the range pi to 2 pi, and x is in the range 0 to pi. So, if you look at this graph of this function is 0 to pi. So, for instance, here we have pi, and then we have 2 pi there. So, 0 to pi it increases linearly. So, here we have again pi, and then from pi to 2 pi it is 2 pi minus x. So, it decreases to 0. So, we have this function, kind of hat function, which is symmetrical around this x is equal to pi. So, it is it is an even function around this x is equal to pi, and then we can apply the result which we have discussed earlier. So, the given function is an even function about this x is equal to pi. Therefore, what we can have, the b n's will be 0. So, b n we have this 0 to 2 pi and 1 over this L, 1 over L and 0 to 2 L, and then f x sin this because the period is 2 pi. So, n x only dx, and this will be 0 without any calculation. We can just set to 0 because this is an odd function around this pi. So, the integral this 0 to 2 pi will become 0, and then if we compute this a naught and then a n. So, a naught is 1 over pi 0 to pi f x dx, and we know the f x is x and 2 pi minus x in this range. So, we can compute this integral. So, here we will have x square by 2, meaning this pi square by 2, and then here we will have minus sign with 2 pi minus x whole square by 2. So, again we will get pi square by 2, and as a result we are getting this pi. So, a naught we have computed as pi, and then we can compute a n as well with the formula 1 over pi and 0 to 2 pi and f x cos n x dx. So, in this case again 0 to pi it is x, and pi to 2 pi it is 2 pi minus x. So, we can again simplify these results, which will give us. So, if we can take a quick look here. So, we have x, and then we have sin n x over n and 0 to pi, and then minus sin 0 to pi. So, x the differentiation will be 1, and then we have again here sin n x over n and then dx. So, because of this sign, and then we are substituting pi or 0. So, this will become 0, and we have the result from here. So, again with minus sign sin n x in the further integration will become cos n x and divided by this n, and again 0 to pi. So, this will be and 1 over pi was sitting there already. So, here n is square, 1 over n was there, and again 1 over n will come, and there is a pi outside this integral. So, when we put this pi, we have minus 1 power n and minus 1 over n square this pi. So, which is exactly written here, and then similarly we can integrate the second integral, which is 2 pi minus x cos n x dx, and then we can further simplify this by taking this 1 over n square common, and this minus will be adjusted here inside. So, there will be just 2 times of the term. So, 2 over n square pi and minus 1 power n minus 1. So, in this case what we have the a n when n is an even number here. So, for instance 2, 4 etc. So, this will become 0, and when it is odd, so then these two will be added minus 1 minus 1. So, we will get minus 2 and then 2 there. So, minus 4 over n square pi. So, having these a n's, now we can just substitute in the Fourier series. This was a naught by 2, and then the rest is coming 4 by pi, and then we have this n square terms. So, 1 over 1 square, 3 square, 5 square and so on, and in this region 0 to 2 pi. So, this the resulting series having only cosine term, because the function was an even function around this middle point pi of the interval 0 to 2 pi. So, in this case one should also note that here I have used this equality sign. Why equality sign is correct here? In this case the function is continuous. So, if we take a look at the function, so this is a continuous function in the whole range this 0 to 2 pi. This is a continuous function, and there its f derivative, we can compute the derivative, and we will notice that that is also a piecewise continuous function. So, we have learnt already the convergence of the Fourier series, and we know that the Fourier series converges uniformly indeed. The uniform convergence was the strongest convergence which we have discussed in the lecture. So, we can write this equality there, that means for any value of x in this range, the series will converge to the function f x, only the end point. But again, if we look at the extension of this function as a periodic extension, so the function becomes continuous also at the end point. So, there is no problem to use this equality for all values of x including the end points. Well, and now we will consider another example where we want to determine the Fourier series of this function f x is equal to x square in the interval minus pi to pi, and then we can use the convergence result to show the these infinite sums, the value of this infinite sums. So, here what we have the x square. So, the function x square in the range minus pi to pi. So, we have minus pi to pi, and we know that this x square function is an even function in this range minus pi to pi. So, again we will get the cosine series, and this therefore, the bn's will be again 0 because of this even function. So, well, this is an even function in this interval. So, therefore, this bn's will be 0 for all n, and then we can compute an's. So, first the a naught we are computing here, a naught is 1 over pi and then minus pi. So, this is minus pi here, minus pi to pi x square dx. Then we integrate here, we have x cube by 3 and then minus pi to pi. So, we can substitute, it will be just added. So, 2 pi square by 3 we will get the result of this a naught, and then we can get a 1 as a n as well in general. So, 1 over pi minus pi to pi, the function f x x square, and then cos n x. So, this also we can because this cos is an even function, x square is even function. So, we can use this 2 over pi and can integrate in the region 0 to pi. So, this integration again we can do with the partial fraction with the idea of this product rule. So, here we have x square, we have x square, and then this cos n x will be integrated to sin n x over n. Then we have minus this 1 over n again, because this cos n x will be sin n x over n. So, 1 over n and then 0 to pi, and we have the function value or the integral of differentiation of this x square, which is 2 x here, and then further because this will become 0 when we put pi or we put 0. So, this is going to be 0 in either case, and then we have the second integral which has to be integrated again. So, here the x and then the sign will be cos, and then again we have the cos there, x will become 1, and then further we can integrate this sign here, which will become anyway 0 at 0 and pi. So, only because of this term we will get the value. So, when x is pi, so pi and cos pi cos n pi will be minus 1 power n and divide by n, and there is a factor 4 over n pi sitting outside. So, what we have? We have 4, this pi gets cancelled. So, 4 minus 1 n square and then minus 1 power n, and then we have this n square there. So, we have 4 times minus 1 power n n square, the value of the Fourier coefficient a n, and all b n's are 0. So, then we can substitute in the Fourier series the a naught and a n's, the b n's are 0. So, we will get this cosine series, because the series will not contain the sine term, and again we can put this equality because this series will also converge in fact will converge absolutely and uniformly, because we have again this x square function defined here from minus pi to pi, and even its extension also. So, everything will become continuous. So, even including the end points, the function in its periodic extension, everywhere it is going to be continuous. So, at any point in this minus pi to pi or over the whole axis, when we have this periodic extension, not just the x square will be extended to over the whole real axis, but in this minus pi to pi, and then we have to extend this, and we should think this as a function, and its period in its Fourier series is given here, and that Fourier series will converge for any point x in R. So, here we have x from minus pi to pi, this will converge to the given function x square in that region, including the boundary points. So, now if we substitute x equal to 0, for instance, in this series, so cos 0 will become 1, and we have the desired series or the sum of the desired series. So, we have 0 there and pi square by 3 and 4 minus 1 power n, which can be written in this form. So, we have minus 1 power n plus 1 n square, the value is pi square by 12. So, if we substitute now x is equal to pi, that we have to see that what is desired values or desired series, and then for what values of x we can get that series. So, here we put x is equal to pi. So, here we will have then minus 1 power this 2 n. So, all the positive terms will come. So, this is the series which we want to evaluate here, 1 over n square, and the value is coming pi square by 6. So, this is a nice application that where using this convergence theorem we can get the value of the series of various series. We will also observe in next lectures again that many complicated series we can get with the help of this convergence result. The further inference here, if we can deduce, suppose this f is integrable, and then what is our aim is to write for instance the Fourier sine or cosine series. So, here the scenario is different now. Suppose the f is given, it is a piecewise continuous or it is integrable, both ways we can write down the Fourier series. So, suppose this f is integrable in this domain 0 to L, and then our aim is for instance to write Fourier sine or cosine series. So, the aim here is different now. We are not writing just the Fourier series, we want to write the Fourier sine or Fourier cosine series. And in this case, what we should do then, we can extend this f to an even and odd function. So, the details of this will be explained in the next lecture. So, just to give some overview and the relation to what we have just done, odd and even function. So, we can extend this f to an even or the to even and odd function, such as we define a new function h x, where the given f x is already there in the interval 0 to L, and in the minus L to L we have made this odd extension of the function. Or what we can do, we can introduce this new function g x as f x, again the same function, the given function in 0 to L, the function was defined in 0 to L, and then in the minus L to L we have made an even extension, so that this g x became an even function. So, this is an even function and this is an odd function. This is an odd function. So, we can do such extensions of the function. The validity of our given function is there in 0 to L. Here also we have in 0 to L the given function. So, we can just think as follows. Suppose there is a function here f x, which is given in 0 to this some range 0 to 1, it is defined by this one, and then there are two possibilities. I mean, there could be many possibilities, but here we are extending, so that the function become this h x becomes the odd function. So, that when we write it is a Fourier series, a Fourier series of h x will have only the sine term, because this is an odd function. So, the Fourier series of h x will have only the sine terms, it will have only a sine series, and when we extend here for g x, which is an even function, and we write the Fourier series of this function, then that Fourier series will contain only the cosine terms. So, we have the expansion of h x in terms of sine, we have the expansion of g x in terms of cosine. But what is interesting, that in the interval 0 to L, where the function is given, we have the same function f x, which in this case will be represented by the sine series, in this case it will be represented by the cosine series, and that is the interesting the so called half range sine or half range cosine series we will learn in the next lecture. Just the last example again. So, in this lecture I have taken this f x is equal to x defined in the region -2 to 2, and the same example I will consider in the next problem, where the interval will be taken as 0 to 2. So, when we take this interval 0 to 2 in the next lecture, our aim will be to write down its sine series or cosine series by extending the function from -2 to 0. So, if we make that extension from -2 to 0 as an even extension, then we will have cosine series, and if we extend that function from -2 to 0 as an odd function, then we will have only sine series. So, that precisely we will be talking about in the next lecture, but what is now here, the function is defined in -2 to 2 and we want to write Fourier series. So, here we are not aiming for a particular series like sine or cosine, here we want to write a sine series, but naturally if we look at this function from -2 to 2, this is an odd function. So, this is an odd function, then naturally the Fourier series will have only the sine terms. So, without any further extension or anything, if we write down its Fourier series, it will have only the sine series. But in the next lecture we will see that if the same function f x is equal to x is given only in the region 0 to 2, and then we want to have its expansion as a sine series or cosine series, then accordingly we have to expand it, we have to extend it in a odd function, as a odd function or as a even function. So, that we will discuss anyway in the next lecture. So, here the aim is to determine the Fourier series, for example, for this function, and as we have seen this is an odd function. So, all e n's will become 0. For b n we have to use this formula 2 over L 0 to L f x sin n pi x over L, and L is 2 here. So, we have 2 by 2 0 to 2 and this x sin n pi x over L. Integrating this by parts, we can we can simplify this b n to this 4 over n pi and the cos n pi, which is -1 power n. So, the Fourier series now, if we write down the Fourier series of f x, this will have only the sine term, and this is exactly we should be clear about it, that in this case we have written the Fourier series of this f x is equal to x function, and the function was an odd function in the given interval. The topic of the next lecture is the defining the half range sine or cosine series. So, there we have the objective that the given function we want to express in terms of the sine functions or in terms of the cosine functions. In this lecture we are just talking about the Fourier series. However, if the function is an odd function, automatically we are getting the sine series. If the function is an even function, automatically we are getting as a cosine series, but in the next lecture we will aim for either for cosine series or for cosine series by extending the function as even or odd function. Well, so this is the sine series, and we have the references here used for preparing this lecture. So, just to conclude again, that if f is an even function, we have a rather simplified version of the Fourier series, where a n can be computed by this formula 2 over L 0 to L f x cos n pi x over L, and if f is an even function we will get only the. So, this is odd function here. So, even function we will get cosine series, and for odd function we will get the sine series where the b n can be evaluated by this function. In the next lecture what we will see now again the how to write Fourier sine or cosine series for f. So, there we will aim for a particular series, we will not just write the Fourier series of a given function that we have already done in this lecture for instance, and what we have observed that if the function is an even or an odd function, the Fourier series takes a rather simple form. Well, so that is all for this lecture, and I thank you for your attention.